Hello, my name is Tom, and I'm here today to present my class project for the data mining course using support vector machines to classify activities. And we're going to be using source data from a brief study out of Australia on passive RFID sensors. We'll go through the background of the uh, analysis I did, a little bit of background on the source data, the methodology, the analysis, discussion of the analysis, and then do a conclusion with a brief demo. So the background is, can we use support vector machines to accurately classify personnel movement, or rather patient movement? And our problem space is some data from a study done out of Australia in 2013. Not a lot of folks, 14 folks, but we had a couple different RFID configurations. So those are the radio frequency identifiers. And there was 8 features recorded, and over time there's about 75,000 observations. And so there's 4 different classes. People could be sitting on the bed, sitting on a chair, they could be laying down, they could be walking. And this is a little bit challenging because it's both a multi-dimensional problem and a multi-class problem. So we want to see how support vector machines would work in that instance. So a little bit more on the context of the source study. We've got a patient sitting on the right, and they've got the actual sensor on their chest there. And in the left pane, you can see how we've kind of mapped the axis. We've got sensor axis as they exist in the data, and then how we've adjusted those to be relative to the patient. So we've got the left and right plane as our x-axis, our bending plane is our y-axis, and then our head-to-toe plane is going to be our z-axis. So for our methodology, there's quite a bit of pre-processing that had to be done to support this. The data was in 94 separate data files, and there was additional features that were inferred from both the directory structure and file names, so whether the patient was male or female, or then in room 1 or room 2. So the ingest routine had to adapt to that and put it in a structure that we could process through quickly. And as well, since support vector machines, as we learned in class, they're very good at doing binary classification, but they don't inherently support multi-class classification. So we had to do kind of a one versus all encoding is what I chose to do. And as well, for a little bit of rigor, I wanted to do kind of a 5-fold cross-validation approach, so just that we could find the best model per activity across those 5 partitions. And the resulting data structure, a subset of that is kind of displayed there. And you can see the call that I actually make when I'm going through the iterations and doing filtering on that structure to identify a stratification group and the positive activity, and then you see some of the features there. So the methodology we used was, as I said, the support vector machines. And as we discussed in class, the history of those actually go back to Ron Fisher with the linear discriminant analysis in the 30s, but the real roots of that go back to the 70s with the theory of pattern recognition. And then the training algorithm for optimal margin classifiers came out in 1992. And in the basics of this, we have a maximum margin classifier that draws a line to separate the classes, and it focuses on the closest points to the separating hyperplane. It ignores all the outliers. Going up to the next level, we have a support vector classifier. But the difference between that and the maximum margin classifier is it actually allows for some misclassification that's not permitted with the maximum margin classifier. Going up to another level, we have the support vector machine, and it's actually multi-dimensional, but we're able to take data that starts in a relatively low dimension, but it may not be separable in that low dimension. So we move it to a higher dimension, and we're able to separate that with a hyperplane and develop a support vector classifier to separate those into two groups. Furthermore, The kernel trick is our specific mechanism within support vector machines that allows us to do this in multiple dimensions. And we've got the actual radial basis function there to the right. That's e to the minus gamma to the L2 norm of U minus V vectors. And we've got a graphic that I leveraged from Josh Stammer's course on support vector machines. And the references are all in the last slide. Our actual call that we make, we use the E1071 package, and we use we took with the activity class, with the bending plane, head to toe plane, the left right plane, and then the signal strength with that radial basis function for our kernel. Our gamma is 5, so that's the tolerance for the disparity in between the classes. And then our cost is our tolerance for misclassification. As I talked a little bit before in the actual processing, I looked at the best model for each activity per stratification group. And you can see all of these here, the best ones are both emboldened and highlighted. And we'll go through the actual particulars here. So the results for sitting on the bed on our the misclassifications are indicated with a blue X. Sitting on the bed was a positive, is a blue, and negative is a 0. And then our dimensionality for the head to toe acceleration, that plane, that's the size of the dot. And furthermore, all of the dots are translucent to 50%, so you can see when things are stacked on top of each other. And for the sitting on the bed class, the accuracy was 94.71%. Our best stratification group was 5. Going quickly through the others, now that we have the pattern, we see sitting on a chair, we had 96% accuracy. For laying down, we had 99% accuracy. And then for walking, we had 98.7% accuracy. So discussing this a little bit, that really looks great. I mean, we're in pretty much the high 90s for most of our accuracy there. But what are some potential shortfalls to that? Well, we only had 14 patients. We had 75,000 observations, but we really only had 14 patients. And arguably, time series would be more appropriate. Most of the intervals were 0.025 seconds to 10 seconds. And further, a little bit of inductive bias on my side with respect to the radio frequency signal strength. I figured that would lend more weight to the good results, so I added that in, but I'm not an RF engineer, so that may have been erroneous, but that's an example of inductive bias. For future analysis, perhaps there could be some A/B tests done between the two room configurations that were in this study, and some explicit outlier analysis. As we talked about before, SVMs ignore the outliers, and there could be some good insights that could be gained by actually doing a more robust analysis of the outliers. And to kind of close out here, it's like, how would we even use this? We said we developed these 4 models, but how do we choose the best one? Well, fundamentally, they're binary classifiers. So if we take an example reading here, we could just run them through all the models. And activity class maps to 3, maps to laying. And as we see here, we run it through, and the predicted class was laying when we run it through all the models. So this actually worked out well. So in conclusion, we provided an overview of the problem space, the methodology, touched on the mathematics behind SVMs. We verified that SVMs do provide a robust solution for classification. We talked about the analysis, some of the shortfalls as well, and we provided a brief operational example. Now we're going to move on to the demonstration, which is just going to be kind of running the code to show that it actually works. And this is available in the SharePoint as well. Just need to make sure that this line is updated, the absolute path to data directory, based on how you expanded on your system. So we're going to hit run all here and pause the video. Come back at the end. And we're back. My system takes about 35 seconds to run. And this is just run in RStudio. It's in our markdown file. We see here each of our results are generated, our overall results, and this is our operational example here at the end. So thank you for listening. Please contact me if you have any challenges getting this up and running on your system, or feel free to just put a comment below and I'll reach back out and get in touch with you. Thanks. Take care.